All right. Yeah, thanks for the kind introduction, Justin. Here's the outline for today's talk. First, I'm going to present an overview and motivate the talk. Then I'll spend the bulk of my time diving into internal details of Soroban, sort of give you a grand tour and also some of the rationales. And we'll tie it all up together in invoking a simple contract and see how it works in action. Then we will end with a quick summary. All right. So what is Stellar Core? I'm sure most of you are already familiar with. Stellar Core is a distributed state machine. So basically, at the heart of Stellar Core is a transaction subsystem that is just a function that takes certain input and produces certain output. And the input consists of a set of transactions, and the output consists of the changes to the ledger which get applied to the ledger, which is a bucket list and SQL. So currently, before Soroban, the available set of transactions are fixed. There are 24 types of transactions: create account, deal with trust lines, etc. And there's a unified language called XDR, or externalized representation. That is a uniform format for different Stellar components to talk to each other, represent data, and transport data. So Soroban is an extension to the Stellar Core's existing transaction subsystem. We want to extend Soroban to be able to run arbitrarily user-provided logic. So in other words, we would like to have a Turing-complete machine that's capable of running arbitrary user code within the existing transaction subsystem. And this is what this presentation is about today. So what are some of the key design philosophies of Soroban? First of all, it must be secure. Any code execution from the guest must be done inside of a controlled, secure environment with well-defined semantics and produces bitwise precise output, because at the end of the day, we want the whole thing to be deterministic and replay safe. It has to be interoperable, because we want running a contract to be able to interrupt with the existing Stellar asset, and we also want the contracts to be able to interrupt with themselves. It has to be performant. Ideally, we want running a contract to be as CPU and memory efficient as running native Stellar code. And as part of this design, we also have parallelism compatible at wherever possible. Last but not least, we want it to be lean, which means we want to include an essential set of features, but we also want these features to be expressive and usable by all contracts. So you may ask, why should I care about this presentation? Well, if you're a contract developer, which I suspect a lot of you are or considering to be, I believe this will help you navigate through different layers of abstraction from how you write your contract and how your contract modified the blockchain state. So, for example, let's take a look at this very simple contract. This is something that usually a contract developer is mostly familiar with, written in high-level language like Rust. Here it's a very simple, straightforward contract that creates some custom data, has a single function here called a power that reads the state from the data, try to do some non-trivial computation, and write it back to the state. And this is usually how contract writers think of their contract. However, what your contract really looks like to the blockchain is something very different. It looks something on the right-hand side. Well, actually, your contract is compiled to bytes code, so it's just zero and ones. But here's just a text format to give you like an overview of what it's composed of. So it's written in WASM, and as you can see, it is already a lot more abstract and a lot difficult to navigate through. And in order to go from the way you write your contract to how your contract works, there are multiple gaps you have to bridge through, such as WASM spec, a lot of host concepts, etc. And the goal of this presentation is to walk you through these these gaps. And hopefully this will also help you make you a better contract developers. And if you're not a contract developer, if you're just a pure academic mind, then I would like to invite you to learn about the novel design of Soroban, where we have made a lot of design choices between expressiveness, performance, and security. So here, so that was just an overview. Now let's dive into the details. So what you see here is a bird's eye view of the internal components of Soroban. I must first point out that Soroban runs within the Stellar core process, so everything is in the same process, consumes same CPU and memory, but here is just the logical separation and conceptual diagram. So within Soroban, it is conceptually split into two halves, the host environment and the guest environment. The host environment implements and profile of features such as host object, contract storage, etc. And these features are made available to the host interface so that contracts can import and use. And on the guest side, the guest is a WASM runtime. So in our Soroban, we choose a WASM interpreter that is lightweight and efficient. So WASM interpreter, it basically runs in a loop and passes and executes the contract code one byte at a time. And there's also a piece of linear memory within the WASM time that is the memory owned by the contract, but is accessible from both the host and guest. So contract can access this piece of memory, but contract cannot access the host memory. And I want to point out this, also we have baked in a native design mode, a native mode where you can directly compile your contract into native machine code, and this allows you to easily debug and step through the code. You're not going to hear anything more about native mode further in this talk, but I just want to emphasize that one of the key design principles of Soroban is to have this easy to debug experience to the user, and this is actually a big piece of the design. So you may ask, why do we have such a split? First of all, because the contract runs in the WASM runtime, which must conform to the WASM specification, which itself is a very narrow language interface. One of the biggest restrictions is you can only pass 64 bits number at one at a time into the contract. So in order for the rich Stellar functionality to work on the smart contract runtime, we need a funneling layer in between. But more importantly, this host and guest split provides a design opportunity, and if done correctly, provides these benefits that we talked about in the beginning, which are security, so that the contract code execute within the guest environment that are controlled, isolated from the rest of the Stellar core. And it provides standardization and interoperability, meaning a lot of the core backbone functionalities can be implemented on the host side and shareable by every contract. And it can be performance because native code runs faster, and it also allows convenient, easy debugging capability for off-chain development. So let's talk about the guest first. So the guest is a WASM runtime that executes the bytecode. So the bytecode itself can be compiled from different source languages. Soroban SDK is one of the main ones, which supports Rust. And Soroban supports WebAssembly 1.0 specifications and only very minor fully deterministic features. So here is a snippet of what a contract looks like in terms of its compositions. You can see there are multiple sections, and I've highlighted a few useful ones. For example, the import section, which contains the host function, which a contract import and it can call. The linear memory, which I talked about, which allows easy data sharing through a shared piece of memory. The export session, which contains a public function that the contract defined exports for others to call. The contract code contains the bytes of the code, and the contract data, which contains the version details and contract specs. Now, so let's move on to the host side. So I'm going to cover several key aspects of the host, including value types, host object, host functions, contract storage, and resource metering. So first of all, an overview of host value type. So the host has its own definition of value, which is a 64-bit integer. So because of the Wasserman restriction, we need a value type that is able to be passed across the host and guest boundary. So we have this 64-bit type. And this integer, this val, we call it val, is polymorphic, meaning that the interpretation of this value can be different depending on the bits pattern. So the value itself is divided into tags and body, and the tag information encode the type of the value and how the body is interpreted. And there are some optimization for small values, which I'll cover in a bit. And so this is a key in host value design, is that for every host value, the host provides native functionality for its conversion to and between XDR. And also for a guest-defined type, it is easily convertible and very efficiently convertible via the host to a host type. And this is all hidden away from the user, so contract writers don't usually have to worry about them, but they are just very core to the development to have interoperable data between different parts. So as mentioned earlier, the value is 64-bit. The lower 8 bits contains a tag, and each distinct tag value represents a different type in the host. And the tag value is further divided in ranges. From values 0 and 15, they represent small values where the value itself can fit into the body. These include void, Boolean, int32, etc. And for tag values between 64 and 77, these are host objects, which we'll cover in a bit. Basically, these are large values that cannot fit into 56 bits, or dynamic structures such as vector map, etc. And we have plenty empty spaces for future enhancement and use. Now, the host object. So the host object is allocated and stored inside the host. They are not directly accessible by the guest, but the guest can access the value that represents the host object. The value itself is the 64-bit value, and the body of the 64-bit value is the handle of the object. They are immutable once created, so any operation that you see that implies modification of a host object actually creates a new host object. So this is also a deliberate design choices that has a lot of considerations, which we will not dive into detail right now, but I'm followed to do a follow-up if needed. Object references can be shared across contract. So this enables efficient data passing and data sharing between different contracts. And in order to access the object, there's an indirection that is required, which goes from the 64-bit value to the object handle, and then look up the object in the host. So the repertoire of host object is the bedrock of Soroban host, which enables complex repertoire of host functions, and these are made available to the contract via the host interface. Now, I've talked about, because of this indirection going from value to handle to the object, the host objects, they are usually much more expensive than raw values to work with. So we have a nice optimization internally for small values. To show you an example, for the external type of int 128 or 128-bit integer, there are two variants in the host. So either if the value is small that can fit into 56 bits, then this value is represented as a tag 128 small value, in which case the whole value is just fits into the 64-bit. There's no host object allocation, no indirection. Everything passes through freely between the boundary. Only when it is a large value that cannot fit into 56-bit, it is tagged as a 128 object. In this case, the host object allocation is involved. So the impact of this is that for a token contract that has to work with a 128-bit integer interface, if they're only dealing with small numbers like low balances, they don't have to pay for the extra cost of allocating host object, which is nice for improving contract performance and reducing the code size. Okay, so how do we go from custom data type to host type? So users normally write their own types in the familiar Rust data types like struct and enum. Here you see an example called state that has two members called value and the exp. So when you write this with the help of Soroban SDK, it is automatically attached with some convenience method that allows this to be seamlessly converted to the host side, to the 64-bit integer. So how is it done? So first of all, the memory of this state object is on the guest side is written into the contract memory. So the key is written as a string and the value into the memory. And there's a host function where it can called map new from linear memory, which converts this memory location and bulk converts it into a host map with the exact same content, but is represented on the host. And this host map is inserted to the object array with a slot number 6, and this slot number 6, along with the tag of the host object type, forms the 64-bit val that is presented to the contract. So in the end, what you see on the left-hand side, which is the rich, expressive, user-defined type, is completely equivalent to the 64-bit that is presented to the host. So we've mentioned host functions. So they are a set of common reusable functionalities that are shareable by every contract. They define the allowed operations on the host object by a contract. And together, they form the public interface of the host. So here are some of the notable host objects. The built-in crypto functions like SHA-256, CHA-20, etc. So we have already a bunch of them. These are typically computationally expensive, and they are mission critical. Most contracts will use some combination of these, and they are usually very kind of difficult to implement. So these are perfect candidates to be implemented as a host function in native code, and they are shareable by every contract. And based on the ecosystem needs, we can easily expand the repertoire of these functions in the future. We have a Stellar asset contract, which are native implementation of the token interface that allows existing Stellar asset to be interoperable with smart contract at native speed. We have events, which every contract can take advantage of generating event, and they can be accumulated in the host, emitted, and these are all XDR compatible and browsable like normal Stellar data. Just a quick mention about the contract storage. You'll hear more about in the later section. So the host can, the contract do not have direct access to the ledger. So they have access to the host functions, but in order to access ledger entries, the transaction that include the contract invocation has to declare the footprint of ledger entries it needs to access. So this footprint is then brought into the Soroban host in an in-memory storage containing all these ledger entries in XDR, and then contract can operate them via the host functions, and in the end, when host finishes, it gets returned to Stellar Core and applied to the ledger. So this design is intended to maximize the compatibility between with parallel execution in the future. So even though right now we don't support parallel execution, it is fully expected and fully compatible. Now, I want to give a quick cover of resource metering. You'll hear more about it in a later afternoon session on fees and metering. So since we allow arbitrary code execution in the host, we need a way to properly measure the resource usage of that arbitrary piece of code. These resources include the CPU and RAM that runs within the same Stellar core process. But this presents a challenge because we have this split world between the host and the guest. On the guest side, it's pretty straightforward. It's just a loop running WASM instructions. But on the host side, everything is just work. So what we have done is we've categorized all the work that host does into a set of non-overlapping components. Here you just see a few of them here. And each component, we use a deterministic linear model that describes its virtual resource consumption of its CPU and memory. And this virtual resource consumption is calibrated against the physical resource consumption. So these models are well reflecting the actual resource consumption of a contract that's running on the chain. And there's a budget in the host that, when running through the code, does the accounting, and then in the end it gets reported for fee calculation and limits application. So the bottom line is the host has a budget system that is comprehensive, covers both the host and the guest work, and this will ensure fairness of contract execution and deters abuse. Okay, so that was a kind of a grand tour of all the host features. Now let's see it all, tie it all together and see it in action. So I'm going to show this simple contract example that I showed earlier. So it's pretty straightforward, I think. It's just a contract-defined data called state with two fields, some alias of the name of the state, which is a symbol, a contract that has a single public method called power, which reads the state ledger from the storage, computes the power given some exponent input, and then in the end write the whole thing back to the ledger. So the computation part is just some computation that you can plug in your own computations, but just here for demonstration. So we will cover through each of these work in details, but I just wanted to highlight that this contract, despite it doing a lot of things, it is only 754 bytes, or roughly 300 WASM instructions, and this is a direct embodiment of Soroban's lean and efficient design. Now, before I start, though, I just want to quickly mention the contract workflow. G did a great job of showing you in real action, so I'm not going to dive into details. So in order for a contract to work, there are 3 steps. You have to upload the code, create a contract referencing that code, get a contract ID, and then in the end, the third step is to execute the code given a set of arguments. So we're only going to cover the third part, which is the execution, assuming the prerequisites have already been fulfilled, and these code instance and contract data already exists on chain. So now let's dive into it. So the first thing you should do is to submit a transaction which contains a invoke host function operation. You see on the top left side. It contains the ledger footprint, which contains the data entries, the contract code entry, the contract instance entry, and the state data. Then the Stellar core will instantiate a Soroban host. So here it has a storage, which contains the entries that you have pre-declared, contract code instance and state data. It has an internal object array that is used for any kind of host object that is needed for execution of the contract, and it implements a number of host functions here at the bottom. This is not a comprehensive of host functions, but just a subset that we will need. So the host then instantiate a WASM interpreter, the VM, which is a WASM guest. So here, the WASM guest has a piece of linear memory, has export functions, which in this case just one function, a bunch of import functions, which it imports from the host, and then the contract bytecode. Here I'm showing you the actual Rust code just for demonstration. Then it will call the function called power, which is the only function here that you can see. Now let's step through this code. The first step is to, the contract will call the get function provided by the SDK, and even internally what happens, this get method will look up the imported host function table and call two host functions here on the left side, has contract data and get contract data. Then the host will go to the storage and find that contract data called state. Notice this state is in the XDR format, so this map is just a representation of the state data in XDR. And then it will convert that piece of data into a host object represented in host map. And then once it has a host map, the slot number, it then returns the value with the type and the reference of the map, returns the value back to the contract. But the contract wants the state type. So how does it do that? So in order to get from the value to the state type, the contract will first write the keys to the memory value exp, and then it'll call this map unpack function given the location of the memory and the value. And it will read, on the host side, it will read the host object that we created in the step before, and then it will bulk unpack the content of that map into the memory, and then the guest can copy this memory into the field, so it has the data it needs. The next step is the power function, which is just it's an easy step, just calls one host function, give it a value, return the value. Now you might ask, oh, why do we not involve any host object? We're dealing with a 256-bit integer. Well, that's a great question. Because of a small number optimization, if we're only dealing with the small numbers in and out, then we can directly use the value. There's no host object getting involved. So this case upholds if we're dealing with small values. So last step, we set the state back to the storage, which is the reverse of the get step. First, write the content to the memory, call the host function map new. It will then read the piece of memory, create a new host object called the new state object, convert that into XDR, and write it back to the storage. And then the last step is we have a storage with the original contract code, contract instance, update the state data. We return the storage to Stellar Core, and then it gets serialized and permanently stored in the ledger. So you can see a lot of the deliberate designs in the host allow us to have a very lightweight WASM contract that is only 754 bytes. So here's a quick summary. Soroban is a Turing-complete extension of Stellar Core, and it has a carefully designed host-guest boundary split for security, interoperability, and performance. The host provides a lean but rich repertoire of shareable types and functions, which allows contract to be performant with minimal code size. And here are some references, and thank you very much.